Or with this fairly new AI agent for conducting a literature review, the Scholar Q&A, we could just provide a topic, and the AI agent will produce the entire introduction or related work of a paper on that topic, which includes references to factual and real published papers. So all of these AI agents, they're reshaping the way how people work. They're allowing them to delegate lower level and repetitive tasks to the agent, which in turn enables the users to focus on higher level tasks that require higher order skills like reasoning or creativity. And this shift has several benefits. It could potentially increase productivity by making tasks faster and easier, and also enables more people, including novices, to perform highly specialized tasks. But this shift in workflow, it's also coming with several challenges. First, AI might make mistakes, and verifying the AI's output is difficult. Second, using natural language introduces ambiguity, making interaction and control difficult. And but yeah, these are so far only the short-term challenges of using AI, verifying and interaction. But if we look deeper, we will notice that these low-level processes that the AI is now automating for us, these have traditionally been processes in which people used to think with, analyze trade-offs, make decisions, solve problems, and even be creative. And with AI replacing such traditional thinking processes, there is a concern that over-reliance on AI can potentially have negative impacts on independent problem-solving skills, which I'd like to classify as one of the long-term challenges of using AI. So in order to address these challenges, in this talk, I'm going to focus on programming as a productivity task that is being significantly transformed by generative AI. Programming languages are powerful types of user interface that drive innovation, automation, connectivity, and creativity. And programming is becoming ubiquitous. It is being used in many tools across different industries and by many people without any formal programming education. In fact, prior research has categorized programmers into software engineers and user programmers like data scientists, business analysts, and even conversational programmers such as UX designers, just to better communicate ideas. But programming is difficult. It requires skills like abstract thinking and understanding the notional machine, problem-solving skills like task decomposition, as well as following syntax and non-intuitive semantics of code. But with generative AI tools like large language models, we're capable of solving many complex tasks from using a simple natural language instruction, especially with tools like GitHub Copilot or ChatGPT that are being used by a variety of different programmers, from software engineers to end user programmers. And with more advanced prompting techniques of large language models, they are able to perform much more complex tasks such as data analysis. So at a high level, when comparing AI-assisted programming with manual programming, we can see the same issues that I identified earlier. Over-reliance on AI in the long term can lead to reduced ability in critically analyzing and engaging with the AI-generated code, and potentially lowering programmers' skills such as task decomposition and independent problem-solving skills. But in the short term, the ambiguities of using natural language for interacting with AI can introduce many short-term challenges, such as difficulty in verifying and controlling the AI to achieve a satisfying solution. So throughout my work, I've been trying to address these challenges by answering the following high-level research questions. First, what is the impact of AI on productivity, over-reliance, and human cognition? And then second, how to build AI tools that protect human cognition when using AI. And then third, how to enhance verification and control when AI agents are solving tasks autonomously. So this brings us to my first project that explores the impact of having access to AI on programmers' productivity. But more interestingly, what will happen when AI is removed afterwards? Can programmers still independently modify, extend, or write code without AI? Or is there a risk of programmers becoming overly dependent on AI? For that, we conducted a study with 69 novice programmers over 10 sessions, one group with access to an LLM for code generation and the other group without. The study started with a pre-test evaluation of participants that evaluated their prior block-based programming skills. And then novices were divided into two groups based on the pre-test scores, the AI group and the non-AI group. Both groups started to learn about Python programming for the first time by working on 45 coding tasks from the basics of Python to more complex topics like conditionals, loops, and arrays. Each of these 45 tasks included two parts, a code authoring part, where the AI group had optional access to the AI code generator, but the other group had to solve it manually. And the second part, in the following that, both groups had to modify their solution to the authoring task manually and without the AI. And for running the study, we developed a self-paced programming environment that provided code generation using OpenAI GPT-3 for the AI group. So in the last phase of the study, we removed AI access from both groups and evaluated their independent coding skills. We first did an immediate post-test, and then a week later, we conducted a retention post-test. And both of these tests evaluated their code writing, reading, and modification skills without AI. So now in terms of results, during the 7 sessions of training with and without AI, the AI group performed significantly better, which is somehow expected. But what is more interesting is to see their independent coding skills on the modification tasks after they had the option to solve tasks with the AI. And what we found was that our results show that the participants in the AI group did not perform worse and even performed slightly better. And looking at their final evaluation sessions on the last 2 sessions of our 10-day study, so on the retention tests that were conducted a week later, contrary to our expectations, we found that participants in the AI group were performing slightly better on all 3 types of evaluation tasks, including code authoring, code modification, and multiple choice comprehension tasks. So this is pretty interesting, but to better understand these results, we looked at their pre-tests and performed a post-hoc analysis and we divided participants into 4 groups. The top 50% group who performed higher on the pre-tests that were conducted in the first session, and the lower 50% group. And we wanted to know what's the impact of AI on these 4 different groups. And what we found was super interesting. Participants in the top 50% groups performed significantly better on the evaluation post-tests if they had access to AI during the training phase. So these are the top students. These were the students that we expected, no matter what, to perform better on the post-test evaluation tasks. But it seems that just because they had access to the AI code generator during the training sessions, they were able to perform much better on the evaluation post-test. But on the other hand, the lower 50% groups, they performed similarly regardless of access to AI. So the results that I'm showing so far demonstrate that AI can improve existing coding skills for some participants, but this was not the case for all. So to better understand the impact of AI on over-reliance, we need to see how and in what ways are participants using AI. And for that, we performed a thematic analysis focusing on the 33 participants in our study that had access to the AI code generator. And we basically looked into their usage patterns of the AI when they were working on the code authoring tasks. And through our qualitative analysis, we identified 4 different coding approaches. Of the total 1,300 tasks that participants worked on during the 7 training sessions, 29% were solved without the AI, so completely manually. But then 46% of the tasks were submitted using a single prompt that asked the AI to solve the entire task, of which about 2/3 of the cases, learners prompted the AI by copying the task description into the AI, while in the rest of the tasks, the participants reworded the tasks in their own words. And the rest of the tasks, participants decompose the task into several subgoals. So they use the AI in a bit of a more iterative way. As some used consecutive AI prompts to solve each different subgoal of the task, while to solve 19% of the tasks, participants used both the AI and performed manual coding to solve the like different parts of those tasks. So this provides a very high-level overview of how participants use the AI. But what is really interesting is the relationship between using these approaches and their subsequent modifying tasks. So just to remind you, each of these tasks had two parts, the authoring and then the modification part. And in the modification part, they didn't have access to the AI. So what we found was the authoring tasks that were completed using the AI single prompt led to the highest authoring score, which is somehow to expect it. But then this was dropped by 30% in the subsequent modifying tasks when they were asked to like code manually. And then we saw a similar effect with the AI step-by-step AI step-by-step coding approach. And then using the hybrid approach of both AI and manual coding resulted in the highest average of both authoring and modification tasks. And interestingly, not using the AI at all for the authoring tasks resulted in a 10% increase in subsequent modification task scores. Okay, so at a high level, what we can see is that using the AI to solve the entire task autonomously led to the highest performance on the code authoring, but it also led to the highest drop of performance when AI was taken away. So in other words, we are seeing some signs of reduced independent coding skills. But how can we prevent this drop of performance? Or in other words, protect human cognition when using AI? So this brings us to my second project, where I took a design-focused approach to design interfaces and interventions that engage programmers in AI-generated solutions as a way to prevent skill degradation. So current AI tools display AI-generated solutions to the programmer and usually include some explanations about how the code works. But engaging with the code or the provided explanation is completely optional. But what if we add a little bit of forced engagement with the AI-generated code? What if we force the users to engage with the code? But so without being disruptive or annoying, it could properly engage the programmer in the generated code, bridging their knowledge gaps effectively and help them apply concepts to similar tasks without AI. We had two important design considerations in our design exploration. A good technique overall should effectively support programmers in understanding the AI-generated code so that they could write or extend code of similar complexity afterwards, while not increasing cognitive load or frustration. And I'm calling this like frustration something as friction. So to systematically explore the design space, we designed and developed 8 different cognitive engagement techniques, each using different ideas to engage the programmer in the AI-generated code. I'll now show you 3 of these different techniques. First, the explain before usage technique. So in this technique, the AI-generated code is displayed to the user, but they cannot use the code into their editor. And the AI highlights different parts of the code and asks the user to answer questions about those parts. And it forces the programmer to answer those before they can use the code in their editor. So the AI asks these short answer or multiple answer questions, and users will receive feedback on their input and have the opportunity to attempt and try multiple times. And once they're done answering questions about different parts of the code, then they can use the code in their editor. The second technique, the trace and predict, it displays the AI-generated code, but it requires the user to trace the code line by line. And at several parts of the code, at several lines, the system pauses and it highlights part of the code and asks the user to predict what will happen, what will be the values of the variables of that line after that line is executed. So it just wants to make sure that the user is understanding how the program works. So for example, here, the user, after they trace through some lines, they're asked about to predict the value of the stack variable here. And this system also asks questions like, why is something initialized to a particular value or something like that? And then they need to just trace the code line by line, look at the variables and trace it. And then finally, once they're done, they could return to their editor and use the code. And lastly, in the lead and reveal technique, the AI does not display the full solution. Instead, it engages the programmer in thinking about what needs to be done at each line of the code. So it provides a very, very short explanation about like what needs to be done at the first step of the code. And then it wants the user to think about, well, what data structure we need to use, or what should something be initialized, or how should we do something. And then once they think about it and predict the correct behavior, the AI then would reveal the corresponding code to that part. And this process will continue until each line of the code is revealed. So here, for example, it asks what data structure should be used. And once they get it right, it reveals the code on the right. And this process is repeated step by step for different parts of the code. And the user is engaging in this iterative dialogue with the AI. And once they get it right, the entire code is displayed, and then they could use it in their editor. So, as I mentioned before, a good technique should maximize understanding but also reduce friction. So, for that, to find the most effective technique, we used an iterative design process with 124 programmers in two studies. We first did 4 participatory design sessions with 4 programming educators. And then a between subject study with 82 programmers using the 7 techniques that we developed. And so 7 techniques and a baseline that did not have any forced engagement. So this first between subject study showed that all of the techniques improved independent coding skills, either manual coding or code comprehension skills, compared to the baseline, which you can see in the green bar in the middle. So basically, all of the techniques had some improvements compared to the baseline technique. But this helped us identify the top 2 techniques, and we used the results from our first study to refine the techniques based on user feedback, which led to the top 2 techniques being the trace and predict and the lead and reveal engagement systems. And then lastly, we ran a within subject study with 42 novice programmers using the top 2 techniques and a baseline with no forced engagement, which I'm going to actually go into some of the details of this study. So we recruited 42 novice programmers carefully to have similar levels of programming expertise. And we wanted them to work on programming tasks that were difficult. That we designed the tasks to be slightly outside of their comfort zone and skill level, so that it would justify the need to use an AI to solve those tasks. In the first phase of the study, this was a within subject study, and all participants experienced using all 3 systems, which were the lead and reveal, trace and predict, and the baseline techniques. And then so we used 3 different programming tasks from 3 different topics to minimize order effect. And for each task, they had to first ask the AI to generate the code for that solution. But then afterwards, they had to engage with the AI-generated code based on the assigned techniques type of engagement. And then they were asked about their perceived ability in writing or extending code of similar complexity to the AI-generated solution. Our goal was to compare their perceived ability, like if they've been able, like after they've worked with the technique, we asked them how confident you are in writing a code or extending code of similar complexity without AI. And our goal was to compare their perceived ability with their actual ability to see how well each of these techniques would help participants in predicting their ability in writing or extending code of similar complexity. So to understand the impact, their actual coding abilities, after they use the 3 systems, in the second phase of the study, we evaluate their actual programming abilities to write or extend code of similar complexity. And for that, they worked on 3 pairs of coding tasks. that used solutions that were similar to the previously AI-generated solutions. So in terms of results, we did not find any meaningful differences in their ability to write or extend code without AI, and they all performed similarly. But in terms of how each of the techniques impacted programmers' ability to in correctly predicting their own ability to solve tasks without AI, we looked into the correlation between perceived ability and actual ability. And what we found was that using the lead and reveal technique significantly increased programmers' ability to evaluate their own performance, while the other two, the baseline and trace predict, did not. And we're assuming this would hopefully, like this higher correlation could potentially lead to more optimal engagement with AI generated code. Now, the other thing that we also wanted to do was to minimize friction. For that, we looked into the amount of frictions that the systems introduced, and we looked into their task load, time during engagement, and how much they were challenged using the techniques. So the trace and predict created the highest task load for the programmers, while the lead and reveal did not introduce more task load compared to the baseline. So that was good. And then in terms of completion time, again, using the trace and predict took almost 3 times more than the baseline, while the lead and reveal took only about 2 times more than the baseline, which is still a lot. But then when using the techniques to engage with the AI-generated code, participants performed significantly better with the trace and predict. Maybe this means that the questions or the types of engagement that the trace and predict was creating was easier, and perhaps maybe working with the lead and like being engaged with the lead and reveal challenged the students a bit more. But eventually, so they were challenged a bit more with the lead and reveal technique. So overall, it seems that the lead and reveal technique improved participants' alignments between their perceived and actual ability without increasing perceived task load. So overall, what does this show? It's showing that potentially engaging the user in the step-by-step process of how the AI is solving the task can potentially be a solution to protect human cognition, as we discussed. So all the things that we've seen so far were programming tasks that were mostly simple tasks that the AI is capable of doing very well. But what if the AI makes mistakes? What if the tasks are much, much more complex? And how do we verify the AI's output? And how do users control and fix it when the AI makes mistakes? So this brings us to my last project, how to improve verification and control when AI agents autonomously solve complex tasks. So LLMs are able to solve these much more complex tasks like data analysis fully autonomously by having access to a summary of a data set and a task description. The LLM can first generate its reasoning for solving the task and then generate a code for it. And then by sending that code to a code interpreter agent or for execution, it's able to display the output results of that code. And this is done through chain of thought and React prompting techniques that have become widely popular. So on the other hand, the most common interaction method with such AI agents is a turn-based conversational modality in which the user has to write follow-up queries to steer the AI if they're not satisfied with the output. Let's actually see a quick example of this conversational interaction. So let's say we have a data set of anime series, and we're interested in their themes and tags. And particularly, we want to know what is the most common tag associated with each theme of all these animes that we have in the data set. For that, we can use a tool like ChatGPT Data Analysis, which allows us to upload the data set and write the data analysis query. And since the AI does not know about the structure and contents of the data set, its reasoning process makes it generate a code that displays a summary of the data set, and then it's executed, and then the AI is able to see the first 5 rows of the data set, and then it's able to use that as a way to build assumptions to generate a code to solve the task. And then the code is executed, and the final response is displayed. But if we look carefully, we can see that there are two tags, military and military, that are one is lowercase and one is uppercase. So that we need to fix this. This is a problem. Like the AI should probably merge these two into one category. But in a conversational AI agent, I don't necessarily need to, like, I could just simply tell the AI that this problem exists without telling the AI how to fix it. So it's just like, it seems that there is both military and military with different casings. The AI would then use this new assumption to retry solving the task, but this time after making every tag and theme lowercase. So what I wanted to show you here is that this process can become much more challenging as the errors become more and more subtle, which actually is the case in many data analysis scenarios. So to better understand the challenges that users encounter when doing data analysis with a conversational AI tool, we conducted a formative study in which 15 data analysts were assigned with different data analysis tasks and data sets, and used ChatGPT with a data analysis plugin to complete the tasks. We asked them to think aloud during the study and analyze participants' usage and think aloud. And we found that first, participants were overwhelmed by how long the AI's responses are and the conversational history. So to help users focus on smaller information chunks at each time, our first design goal was to prevent the AI from autonomously solving the entire task. So instead, we wanted the AI to solve the task using multiple intervention points and progressively revealing those intervention points and responses. The second challenge that we observed was that participants spent a lot of time understanding why the AI has generated a code. So they read the code and like they try to meticulously find why the AI has like been generating that line of code, or and then they wanted to infer the AI's assumption by doing that. So to address this, our second design goal was for the AI to explicitly generate and display its assumptions using editable UI components at each intervention point. And the third challenge that participants faced was that they used the follow-up queries in the main task thread that were unrelated to their actual task. For example, they wanted to do the data exploration, code exploration, code explanation, and output verification follow-up questions in the same conversation thread. And what the problem was that this made their conversation history much more cluttered and difficult to understand. So to address this, our third design goal was to support users to run side AI queries at each intervention point so that they could do these explorations without cluttering the main conversation thread. So to build a system that would address these design goals, the AI should decompose the task, right? Like we don't want the AI to solve the task immediately in one go. But how should it decompose it? How many intervention points should the AI create, and at what levels? How much information to display at each intervention point? And how structured should the display of information be? For that, we, based on prior research and our own experiences using and building AI-powered tools, we designed two new systems: the phase-wise system that decomposed the task into different abstraction levels, and while the stepwise system decomposed the task into a sequence of sub-goals until the task is finished. So both systems start with a simple input data set and query, and the system automatically creates a comprehensive summary of the data set. For the LLM, it basically provides a textual information about each column. Now let's talk about the phase-wise system. It decomposes a task into three abstraction phases: input-output assumptions, execution plan, and code and output. In the input and output assumptions, it retrieves all the relevant columns to the data set based on the user query, and it displays all the assumptions about the task for those columns in a structured way. And everything is editable here, including editing and adding new assumptions, adding or removing relevant columns to the tasks, and even the users can even inspect each column for more details, including descriptive stats. So once the user is satisfied with the current state of the input-output assumptions, they can hit the next button to generate the next phase, which is the execution plan. It's basically a natural language plan of what the AI wants to do. Users can edit, move, and select from optional steps in this plan. And once they're done with this phase, they can move on to the next phase, which is the code and output. And this code is editable, and if the user is not satisfied with the answer, they can either edit the code directly or go back and edit previous steps, which would then require the system to regenerate the preceding steps. Now let's look into the stepwise system. Here, the task is decomposed into multiple sub-goals, solving the problem one step at a time until the task is finished. So each step has two components, assumptions and actions, as well as corresponding code and output, which corresponds to the assumptions and actions. At first, it simply reads the data set and the user can simply inspect any intermediary variables. And then it generates its initial set of assumptions for the second sub-goal. So these are assumptions that are formatted to show the assumptions and its corresponding action. So like something like some tags have white spaces, and then the action is use this to clean the data to clean those strings. So once the user is happy with the assumptions after editing them, the AI would then generate the next step, the corresponding code and its execution output. So basically, this process continues step by step until all of the task requirements are satisfied, and then we have the final solution. We also developed two features to allow users to perform side operations during the data analysis process. In both systems, users can also run side queries to perform data explorations. On the side, they could draw a histogram ask the AI to draw a histogram about the data without derailing from the main conversation thread. So these side queries are in natural language, are executed and displayed in the side of the interface. They can also select parts of the code that was generated to ask for explanations or modify the code using a natural language prompt. But in order to evaluate the effectiveness of these two systems that we developed, we also developed a baseline, a conversational baseline system similar to ChatGPT. And it basically solved the task with no intervention points, and nothing was editable. And the only way of steering this baseline was to ask follow-up queries. Again, similar to ChatGPT. So for evaluation, we ran a within subject study with 18 data analysts in which they worked on in 6 data analysis tasks. And what was super cool about this study was that we designed the tasks in a way that were that the AI would normally produce incorrect responses if the users did not involve and engage with the system. So basically, we injected 2 issues into each of the tasks, and we required users to verify the output and steer the AI whenever it's doing something wrong and fix it. So in terms of results, in terms of performance results, like verification accuracy and time and task, unfortunately, we did not find significant differences. However, in terms of perceived ability that was measured through Likert scale questions after using each of the systems, both the stepwise and phase-wise systems were perceived significantly better in terms of both how easy it was to verify, how easy it was to intervene and fix, and their sense of control over the AI. Almost all participants appreciated the ability to directly edit the AI's assumptions and aligning the system's operations with their own expectations. So this is a quote that I really love about our study. I could add any assumptions that I had in my mind and make it the AI's assumptions. So looking deeper at these editable assumptions, participants found that when the system's assumptions were editable, like the stepwise or the phase-wise systems, they tended to be more critical towards the assumptions. And then, however, when the assumptions were not editable, like in the baseline, they actually tended to accept them without even questioning them. And it was also a source of frustration and lack of control. On a different dimension about how structured the information was displayed, We found that with more structure, like the phase-wise system, users found that they had finer control over the AI. It helped them find information easily, but it was also a source of information overload. But with less structure, like the stepwise system or the baseline system, they found that it's difficult to make targeted edits. So we also found that additional that smaller steps in the process, like the one that was used in the stepwise system, it improved participants' confidence as they were not scared of making edits. They thought about every step of they thought about verifying the AI's output at each step along the way, and also felt more similar to how they would approach their own data analysis process. But interestingly, there were also several participants that liked the baseline, the conversational interface for some situations. Particularly, they mentioned that they felt less critical about their own edits. And then it also had an easier mental model, and the AI would produce faster feedback. So while both systems were preferred over the conversational baseline, overall our results are showing that the stepwise system was the most balanced. It improved confidence and and sense of control while also supporting verification during the process without creating too much information overload. Okay, so now let's take a step back. What does all of this mean? At a high level, it seems that when AI agents are solving tasks fully autonomously, this fully autonomous way of solving tasks is actually the source of two types of challenges that we identified earlier. The short-term challenges of verification and controlling the AI, as well as the long-term challenges of reducing independent problem-solving skills. But interestingly, our results in design explorations are pointing to a single solution, at least for now, that could potentially solve both of these challenges. And that is by preventing the AI from autonomously solving the entire task, and instead involving the user in how the AI is solving it, allowing users to understand the AI's assumptions throughout the process and make them and be able to help them check and verify those assumptions and fix them whenever they want to. This could not only improve short-term productivity gains, but it would also potentially help prevent long-term skill degradation. So, a question that I would like to ask and leave, I guess, is that does that mean that we do not want any autonomous AI agents? Does that mean that involving the user in the AI's process is always better? No. I personally believe that it depends on the amount and complexity of the assumptions that the AI is making when solving the tasks. So what do I mean by the amount and complexity of these assumptions? Basically, I'm focusing on those assumptions that are unspecified by the user. They're not mentioned in the original prompt, and therefore the AI had to guess about them and come up with the best assumption for those. And these unspecified assumptions these are difficult, and these are used by the AI to make decisions for solving the task, but they are difficult to understand why the AI is making those assumptions. They're difficult to verify. How should the user check and whether those assumptions are correct? And how should they fix and steer the AI and correct it when it's having the wrong assumptions? I personally feel like this is the problem that needs to be solved for the future of human AI interaction and AI agents. Future tools could either reduce the number of unspecified assumptions that the AI is making by creating new interfaces and interaction modalities that encourage users to properly specify details when writing prompts. So for example, what if we could combine direct manipulation interfaces and natural language interfaces and help users to refer to things, refer to existing elements in the context, or refer to the capabilities of the system, or even help users in the task decomposition process. Additionally, future tools can make the user more aware of the AI's reasoning process, similar to what models like DeepSeek R1 are doing right now. They could find the most important assumptions and display only those to the user. They could also display the AI's confidence score about each of those assumptions and let the user verify and decide between different options. And lastly, how can we help users in exploring different assumptions, comparing the different outputs? What if future AI tools had a debug button on their outputs that we could like help users test and audit the final response? And with that, I would like to thank you for listening. And I think there is a couple of minutes for questions.